All right. Hi there. Oops. I hope everything's going good. I hope you deal with the first couple sections. I hope it wasn't too painful for you. Like again, hey, just a few things. Just I wish we could be together again. Here I am sitting in my son's room right now. Um, but it is what it is. So, hey, I don't know if y'all have any good stories. By all means, come to, if you're getting some good stories. If you're getting to watch classes or something like that, feel free to come into the office, give me some good stories. I've got some crazy ones already. School's already kind of bizarre. High school's all over. If you aren't willing to change per day, you're going to fall behind. So, just FYI, that's the way we are going. So, let's get into, we're going to get into 9.3 here. So, let me go ahead and get this started for you. And let's see here. Are we going to go? There we go. All right. So what we're going to be talking about is simulations of probability and odds. Expected value, I don't do a whole lot with. I don't think you're going to see anything. Most of the stuff you're going to see is a little bit on simulations. I don't do a whole lot of simulations because really it takes so much work. But we'll kind of just explain it to you and how it works. Odds is the one that we are going to talk about. That's kind of where most of your questions on this section is going to be from. All right, simulation is a technique used to act out a problem by conducting experiments whose outcomes are analogous. I can't say that word, but to the original problem. Remember, I am a math teacher. Now, basically, it's we use simulations so students typically estimate a probability by using many trials rather than determining probability theoretically. We talked about theoretical probability the other day. That's what it's supposed to be, and then you have experimental. So a simulation is basically a form of experimental, except it's done at more of a random rate. Okay, and so what they'll do is they'll make random digit tables. If you see this one, this is just an example of one. It's randomized by maybe a computer or calculator. Can't really do it by hand because it's not very random. So you look through here, you have 5 digits, which probably means there's going to be 5 trials, and each number is going to represent something. Okay, evens might represent something. Odds may represent something else. They may do prime numbers. They may go 0 through 5, or 4, and 5 through 9, depending on how you want to use the table. Okay, if you use even and odds, and you're counting the even odds of this first trial, you have one. You have basically 4 evens and 1 odd, so you have a 4 and 5 chance. And so you're just looking through and you're getting all these estimations. Okay, really hard. Some of the things it says here, the way they use in this one, it says simulate a coin toss, pick a number at random to start, and then read across the table, letting an even digit represent heads and an odd digit represent tails. So you can just pick any number and say like this one here, 39968. So that would be 3 odds, which would be 3 tails and 2 heads. And you can calibrate all of these in the same way. Okay, and then you can get a percentage as you go through all those, and take a tally of all the percentages and get an overall probability of tails over heads. Now, theoretically, the more you do that, you should still get close to 50-50. Now, here's another example. A baseball player, Reggie, is batting an average of 400. This gives his experimental probability of getting a hit on the particular time at bat. Okay, it's experimental because that's how he's been hitting. Okay, Astros hitters, they have an experimental probability of getting a hit because they're taking the stats on it. Estimate the probability that he will get a hit, at least one hit in the next 3 times at bat, if the at bats are independent events. In other words, each number is going to be an individual at bat. Use a random table. The hit is represented by the digits 0, 1, 2, 3. Now, why is that? Is because he's right now hitting 400, which means 4 out of every 10. So there's 10 digits. They're picking the first 4. 0. You can pick any 4 digits you want. they're using 0, 1, 2, 3 to be their hits, and the other 6 numbers are going to be outs. Okay, so when you look at it, in these 3 at-bats, he got 1 hit. In these 3 at-bats, 1 hit. Down here, he gets 2 hits. Okay, over here, he gets 3 out of 3 hits. And so you're getting a random of all of these, and they take those numbers. Okay, so there are 42 out of 50 trials. There's 50 trials here. There are 42 of them in which he has at least 1 hit. So every number that has a red in is at least 1 hit. So that's a 42 out of 50. So an 84% chance he's going to get at least 1 hit. Okay. Says here, suppose Corey makes enough batter for exactly 100 chocolate cookies and mixes 100 chocolate chips into the batter. So roughly 1 chip per cookie. Ugh, I want multiple chips. If the chips are distributed at random and Kwan chooses a cookie at random from the 100 cookies, that's the probability that it will contain exactly 1 chip. So in this random, it's constructed 10, it says constructed 10 by 10 and represent 100 cookies Corey made. Each square can be associated with some ordered pair, where the first component is the horizontal scale and the second is the vertical. Use a random digit table to create ordered pairs, and then create a tally in the grid to represent each chip. So basically, 0 through 9, 0 through 9, there's 100 squares. Okay, and then the randomization of it is what they build. So here's your random. Okay, it says estimate the probability cookie has exactly 1 chip. So you have to count how many of these have exactly 1 chip. Kind of gets a little tedious, but it's 34 out of 100. And whoops. And so that's the probability of exactly 1 chip. Okay, some of these cookies do not have any chips because some of them have 3. And so this is randomized by a computer. You can't just pick them. I mean, I guess you could roll it, flip. I can't flip a coin. You got what? That's 1 through 3, or if there's a couple of 4. So this is just all totally computer randomized. All right, odds. This is the one we're going to talk about a little bit more. Okay, because we're going to talk about odds in favor and odds against. Okay, this is what you see at racetracks. Okay, those kind of things. They want odds in favor and odds against the horse for winning. Those kind of things. You see a 3 to 1 chance or a 1 to 3 chance. Okay, so you have an odds in favor, which is the probability of something happening over the probability of something not happening. Remember this little line over here, like something not happening. Okay, so instead of the probability in regular probability, it's the probability of something happening over all the outcomes. Okay, this is a little bit different. Okay, this is favorable outcomes over non-favorable outcomes. Odds against is probability of something not happening over the probability of something happening. Okay, and we write them in different ways. Now this is the normal way, right? This is how I kind of usually teach it. Odds in favor of outcomes over the number of unfavorable outcomes, and vice versa, odds against. Okay, so a couple examples for you. Okay, so let's just try it this way. Find the odds in favor, and that's a key. You got to make sure it's odds in favor. So that's going to be, let's go here. So this is going to be the yes, the number of good times over the number of bad times. Okay, so find the odds in favor of a given event, rolling a number less than 5 on a die. Well, that would be 1, 2, 3. Whoops, that's a bad 3. And 4, right? Those are all less than. So how many of these are less than? There's 4 of them. Okay. So there's 4 of them. So that should be 4 to 2. Okay. So think about this. The 4 is the ones that work. The 2 is not. Okay. which reduces to 2 to 1. Okay? Now, one of the things I want you to look at is, as we look at these, see this number here? 4 plus 2 is 6. How many numbers are there on a die? There are 6 numbers on a die. These two numbers should always add up to the number of outcomes. Okay? Now, tossing heads on a fair coin. Well, you have one is a heads and the other side is a 1. So you have a 1-to-1 odds in favor, okay, or a 50-50 shot, okay? Anytime you get these two numbers to be the same, the favor over the other, it'll reduce to 1-to-1. This is where they will always be a 50-50 shot. Okay. Now rolling a die is fair because there's 1 out of 6 every time. Right. Okay. So all of these things is where we go with it. All right. All right. Find the odds in favor of a given event. Drawing an ace from an ordinary 52 card deck. How many aces are there? There are 4. So the odds in favor are 4. Okay, now what do we remember about how it should look? 4 in favor, 48 against. Or, remember those two numbers should have to add up to 52. After you figure that out and make sure it adds up the number of outcomes, then you can reduce it. Okay, a 4, and it's basically another way of writing odds. They're using the colon or whatever. Okay, you can also write odds as the fraction and it reduces like fraction. Okay. The only thing is if you get something like 4-to-1, you still have to write it 4/1. Okay. Drawing a heart from an ordinary deck of cards. How many hearts are there? There are 13. Okay. 13 out of 39. Notice these two still add up to 52. And then 13 and 39 reduces 1-to-3. Okay, so for every 1 heart I pick, I probably am going to pick 3 that are not hearts. Okay, let's see here. I need to, whoops, I lost my thing. All right, whoops, that's not what I do. Hold on. I need to clear and then get rid of. All right, here we go. All right, so here's another way of showing odds in favor. It's the same thing we were talking about. Okay, computing odds. If odds in favor of the event are m, the n, then the probability, now this is probability, is going to be favorable over the total outcome. And so this is still probability. It's the same with probability, except odds against is the things that don't happen over the number of outcomes. Okay. Expected value, we're not going to talk about much, so I'm going to go through that, and I think this is kind of interesting. Just to kind of explain, I don't have any questions on that, but I'm going to finish off with this. Okay, it says it costs $5 to play a game when 2 coins are tossed. You receive $10 if 2 heads appear, $5 exactly with 1 head, and nothing if no heads appear. Is this a fair game? That is the net winnings a possibility of 0? So I found this kind of interesting. I haven't done this too often. Probability of a head-to-heads on 2 coins is 1/4. Probability of a heads-tails either direction is 1/2. And probability of no heads is 1/4. So to figure out if it's a fair game, we're going to put price value. We're going to put how much money you're going to make on each of these. And if it equals to $5, it's a fair game. If it doesn't equal if it's more than 5, then it's an unfair game. So 1/4 is $10, 1/2 is $5, 1/4 is $0. So that's going to be 5/2, 5/2 is a grand total of $5, which means it's a fair game. because what you're putting into it is the probability of getting back out of it. It's just kind of interesting. So that is that section. Hopefully that helped you. I'm going to stop sharing that. And we hope that this will be good for you. Okay? We'll see y'all later. And oh, one other thing, just give me time to get the grades all settled and trying to figure out to make sure everything from my math lab on your assignments get over to your Blackboard in the right percentages. So it's kind of a little tricky, but it'll get done hopefully before the first test so that you'll know what you're doing. All right, see you later.